Hi, my name is Gabe Wilson, and today I'm going to talk to you guys about cellulose. So cellulose is basically from a basic unit of cellobiose, and cellobiose is basically two glucose molecules combined, and they're linked at 1 and 4 in a beta formation. Cellulose is interesting because it is the most abundant carbohydrate that we will consume from plant material, and that is because plant wall and cell walls are made up of 30% cellulose. And of that 30% cellulose, 70% of the cellulose is going to be in a crystalline formation, where 30% is going to be an amorphic formation. And a crystalline formation is basically a very tight linear bundle of multiple molecules running through there, long chains of this. We're talking up to 300 units of cellulose. And so basically, if you imagine a pencil, one pencil is not very strong, but when you have 20 pencils together in a big linear chain, it's going to be hard to break. And that's where we come into with cellulose being insoluble and indigestible in our bodies. It's also known as a dietary fiber because our bodies do not have cellulase, which can break down cellulose. And the amorphic formation over here, that 30% amorphic formation, is more of a branched formation, a little bit more free and not in that total tight linear bundle. So, like I said, because of that linear crystalline formation, it is insoluble. If you look at a raw cellulose molecule, you can see that there are 3 OH groups that theoretically can be derivatized, but since it is insoluble and those crystalline formation, the high molecular weight, we cannot derivatize it in our body. Although there are some reactions we can do to do that. The first reaction we can do is an acid hydrolysis, and we can take that cellulose and we can combine it with a strong alkali, and it forms a microcrystalline cellulose. And this microcrystalline cellulose can be in 2 forms. The first form is a dried spray form, and that's going to be larger crystal molecule size. It's going to be porous, and it's going to be kind of sponge-like. So we can take this dry spray microcrystalline cellulose, and we can use it for cheese. We can put it on cheese as an anti-caking agent, and that can help the cheese from sticking together and becoming, too much moisture inside of there. And the second form of this microcrystalline cellulose is a colloidal cellulose. And the colloidal cellulose is going to be a little more mechanical energy involved to break it apart, to break those weak parts away from that cellulose molecule. But once we do this, we can actually then use the colloidal cellulose to form these thixotropic gels, which we can use to strengthen foams in the food industry and strengthen emulsions as well. So, although microcrystalline cellulose is not soluble, we're still not soluble yet, but we can still add it in another reaction to make it soluble in water. And we can do this by then, after that alkali reaction, after that acid hydrolysis, we can take it and we can throw some chloroacetic acid in there. And what that chloroacetic acid is going to do is it's going to break up those hydrogen bonds that are holding that crystalline cellulose together. And when those hydrogen bonds, when they break, that cellulose is going to become more soluble. It's going to become a little more workable. So the reason why those hydrogen bonds break up is because of that high degree of substitution. And that degree of substitution is above above 0.4, which causes it to be water soluble. And this step, the product of this step is carboxyl methyl cellulose. And carboxyl methyl cellulose is going to have a higher viscosity due to those adjacent chains, the repulsion of those adjacent chains. So we can use this again for foams and gels as a good thickening agent as a good gel. And so the next step, we can even go farther here. And after that alkali treatment, alkali cellulose treatment, we can then treat the cellulose with methyl chloride. And when we treat the cellulose with methyl chloride, we get methyl cellulose. And if we treat the cellulose with methyl chloride and propylene oxide, then we get hydroxypropyl methyl cellulose. A mouthful. But basically, now we're looking at cold water soluble cellulose, and that is due to the ether groups breaking up those hydrogen bonds, and really those internal hydrogen bonds. So now we're not just on the outside; we're getting to the inside and breaking up those hydrogen bonds. This can give us a thermal gel. At a room temperature, it's still solution, but once we reach 55 degrees Celsius, it can become a gel and start gelation. Once we go back to room temperature, it will decrease again back down to solution. Now, when we do this, we have gums in our food. We can use these gums, and also it can be used as a fat replacement. So I hope you learned a little bit more about cellulose. Thanks.